Hi everyone. At this point, we have already taken a look at a couple of patterns between taking the derivative of f of x and just kind of looking at what patterns happen, especially dealing with the constants that are in f of x and how they disappear. So we've already kind of talked about that for a little bit. We've talked about the idea of anti-differentiating or integrating means that we're determining a general function that works for a specific derivative. And this does include that plus c that we need to account for any constants that may disappear. And we've already gone through and practiced a little bit saying that these are the derivatives, what must be the antiderivative. So we're going to look at a couple of new notations too that go along with these types of problems. So if you'll notice here, we are bringing back the integral symbol that we were using for area under the curve. So in here, we do have this integral that's right in here. And because this particular integral does not have the limits on there, they don't have those little numbers at the bottom and the top. This is what we call an indefinite integral. And it basically just means that we're not necessarily finding a specific area between two different bounds because we don't have those numbers on there, but it basically means that you're going to find the antiderivative. So you're starting off with a function and you're going to create its antiderivative function. We're not going to find a specific area. So for an indefinite integral, your response will not be necessarily a single value, it will actually be a whole function. And we're going to always make sure that when we see the indefinite integral, that we include this plus c at the end because we are coming up with a general equation. So the next part of this that we're going to take a look at is the g of x part right in here. This is what we consider our integrand. And that integrand is basically representing your derivative. It's kind of like your first derivative, or maybe it's a second derivative equation, but it's basically the derivative. And we wanted to try to come up with a function that would have g of x as its derivative. So over here off to the side, where we have our f of x plus c part over here, let's change that color up a little bit. Let's bring back the pink. So this f of x plus c part over here, that is considered your antiderivative. So when we see an indefinite integral, it means we're going to try to come up with what the antiderivative expression is going to be, and we're always going to include that plus c with it. So if we take a look at these other two examples that are underneath there, these are some of the examples that are telling you, find this antiderivative. I'm giving you the derivative. I want you to go backwards and try to figure out what function it might come from. So in here, if we highlight just what the integrand is, here the integrand is an x squared. Over here, the integrand is a 2 pi r. Now, something that you want to take a look at is what that variable is on the very, very end. So here I have dx on the end, and in the other example, I have dr on the end. These represent what variable you're integrating or anti-differentiating with respect to. So that means in this first example with the x squared dx, the variable we are working with, our independent variable, is x, which means that when we took its derivative, x was the item that was following all those power rules and those chain rules that we were following before. So in this first example, we can just say that, okay, this had to come from, we have a derivative of x squared, so that's following a power rule. It would have come from x to the third, and we would need a coefficient of 1/3 to help balance that out, and of course the plus c. For the second example, since we have an r, it means r is the variable, not an x this time. And since I see the r that's in here, that's where my power rule is going to come from. That's r to the first, so I would need r squared. And since I'm going to take this 2 pi and divide it by that new squared, I just end up with pi. And of course, we're going to add that plus c at the very, very end. So when you see these types of problems, you see these indefinite integrals that don't have the numbers at the top and the bottom, they don't have those limits. We are basically, it's our symbol to tell us we're going to find the antiderivative, or another word for that is to integrate those particular expressions. So here's a couple of basic rules for anti-differentiation that we are going to be following and using. If your function is on the inside, the integrand part on the inside is just a 0, we know that that has to come from some sort of constant value. If we end up with some other value other than 0, such as like a -4 or maybe a positive 127, or that's what this k here represents, some other kind of scalar number, it had to have come from some expression that is k times x plus that constant. In other words, the derivative of kx plus c would be just k. If we're looking at our power rule, we have x to the n. So what's going to happen is we're going to have to raise that exponent by 1. So we're going to do n plus 1 for our new exponent. But we're also going to need to make sure that our coefficients become adjusted as well. We're going to have to take whatever coefficient we had, which in this case was a 1, and divide it by our new exponent n plus 1. We're also going to include a plus c, as always. Now, for sine of x, its derivative is positive cosine, but we're trying to find what function has positive sine as its derivative, and that comes from a negative cosine of x, again with the plus c. And finally, for cosine, in order to have a derivative of cosine, we need to have a positive sine of x plus c as our antiderivative. So lastly, we're going to walk through just 4 examples, or actually 6 examples, it looks like, or actually just 2. We're going to walk through 2 examples, and you're going to try out the rest of them to try to anti-differentiate each one of these expressions in here. So for letter G, it looks like we're following a whole bunch of power rule in here. We've got a 2x to the third, a 5x, and a -4. That's all a polynomial. So we're going to use the power rule. So for this very first term, we have x to the third. It's going to be raised to x to the fourth. And we're going to have to take that 2 and divide it by that new exponent of 4. For the next one, this is x to the first, so it's going to be raised to x squared. And the 5 is going to have to divide by that new exponent of 2. And then the 4, this is technically x to the 0 power, but here we're going to say this is going to be -4 times an x, since 4 is just a scalar number. So we can reduce this a little bit, and we're going to say it's going to be 1/2 x to the fourth, 5/2 x squared minus 4x plus a c is going to be our antiderivative. Now with something like letter H and something like letter I, you would want to go through and actually use some algebra to kind of simplify those expressions where possible. Same thing actually with letter J. We're going to take a look at letter I first. So we're going to manipulate letter I. We're going to do x to the -1/2 times x plus 6 is that same expression in that integrand. I'm going to distribute that x to the -1/2 to get x to the +1/2 plus 6x to the -1/2. And now I'm going to take the antiderivative. So first up is x to the 1/2. If I add 1 to that exponent, I'm going to get to the +3/2. I'm going to have to divide 1 divided by the 3/2. The next is 6x to the -1/2. I'm going to have to add 1 to that -1/2 to get +1/2. I'm going to have to take the 6 and divide it by that 1/2. So we do have some simplifying to do with those complex fractions. The first one ends up being 2/3. We'll have x to the 3/2. And the next one, when I simplify the 6/1/2, we're going to end up with a total of 12, x to the 1/2, and include that plus c in there. So take a look at these other examples for H, J, K, and L, and then also take a look at the problems in Delta Math, and we will reconvene tomorrow to see how it goes.